Hello, everybody. My name is Julian, a PhD student of UC Davis. And today, I'd like to share with you our investigation of hardware managed DRAM caches and why they just don't work with terabyte scale NVDIMMs. So, we have these terabyte scale NVDIMM systems that can be very beneficial for terabyte scale applications. But coupled with these systems are hardware managed DRAM caches. So we asked the question, well, what sort of impact to performance do these DRAM caches have on these sorts of applications, and why? In order to answer this question, we try to understand DRAM caches by applying a variety of micro benchmarks on real hardware in order to identify the basic performance characteristics as well as limitations of these devices. We then take these insights and show that they manifest themselves in real world workloads, such as graph processing, as well as how they impact their performance, ultimately finding a 50% reduction in bandwidth utilization, as well as 3 to 5 times more data being moved, thus coming to the conclusion that DRAM caches just don't work well, especially with these applications whose working set size greatly exceeds the capacity of the DRAM caches. Now I'll be going over the motivation for our work, as well as what others have done in this space. We have emerging applications that are constantly growing day in, day out. Just last year, OpenAI released GPT-3, a new machine learning model that requires hundreds of billions of parameters in order to train, easily exceeding the memory footprint of 350 gigabytes. On the other hand, we also now have graphs that require the processing of hundreds of billions of edges, easily matching up to terabytes worth of a memory footprint. And so, this is of major concern for data centers and high performance computing areas alike, given that they have to accommodate for so much memory in order to enable these sorts of applications. The problem being, well, DRAM is expensive, and at this scale, it's really expensive. So, in order to address this, Intel has been releasing servers equipped with NVRAM devices, specifically Intel Optane DC, because of the fact that, well, compared to DRAM, they're much cheaper per byte. They come in models with much higher capacity. They're both persistent and byte addressable, so they come in a DIMM form factor and can sit as your system memory. But we can't simply replace an all DRAM system with an all NVRAM system due to the fact that they have much higher latency and much lower bandwidth. And so to get around this, Intel has also been coupling with these systems a smaller footprint of DRAM that can act as a cache in what's else known as the 2LM mode, as is tradition in order to mask the higher latency of the NVRAM devices, creating this heterogeneous system. And there's been a lot of work trying to understand these heterogeneous systems, specifically from the NVRAM point of view, from the system level. A group from UCSD had performed an in-depth performance review of Intel Optane DC, identifying their performance characteristics, while also having developed a simulator that modeled and analyzed the microarchitecture of these devices. From the application point of view, there's been a lot of work trying to bridge the performance gap between an all DRAM system and these heterogeneous systems, specifically with AutoTM, who optimized the performance of CNN training by taking advantage of the movement of live tensors, and Sage, who boosted the performance for graph processing by limiting the amount of writes to the NVRAM devices themselves. From the DRAM cache point of view, there's been a lot of work understanding and studying DRAM caches generally, such as Alloy and Lowe-Hill, who looked at a variety of different designs as well as their trade-offs, and Baer, who showed a way to reduce the bandwidth consumption of DRAM caches. But ultimately, these research or these studies have been primarily focused on simulated DRAM caches and DRAM caches at the scale of at most 1 GB in size. And so what we're interested in is what about these DRAM caches that are orders of magnitude greater in capacity in order to accommodate for these terabyte scale NVRAM systems? How well do they perform and what sort of limitations do they face in this kind of system? And so now, in order to understand this, we go over an analysis of a real implementation of a DRAM cache and the insights we gathered from micro benchmarks we ran on them. So we studied a specific implementation of a DRAM cache given to us or provided to us by Intel in the form of a two-socketed Xeon server that contained 384 gigabytes of DRAM as well as a 6 terabyte NVRAM. And what we knew about how the DRAM cache was implemented in this system, we knew that it was a direct mapped cache based off of Intel's own document, but we also expected, given that it's fairly common among DRAM caches, that this DRAM cache would also suffer from additional DRAM accesses, otherwise known as access amplification. And what is access amplification? Well, just to make sure we're on the same page, I'll go over an example of how access amplification may manifest itself within a simple implementation. But generally, in the ideal case, when you have a program that makes a demand request or tries to access some data, you would hopefully only have one memory access. But generally, what we encounter instead is there are multiple memory accesses per demand request by the program. And so imagine, if you will, we have a system and we have a write miss to our last level cache. What may occur is then we make one memory access to the DRAM cache in order to check whether or not the data lives there. If it does, we get a hit, we make another memory access, and we write and update the data in the DRAM cache. If we have a miss, if we have a dirty miss in particular, we then have to make a memory access to the NVRAM device in order to write back the dirty data, and then we can make another access to the DRAM cache again to update the data there. And in this simple implementation, we observe at most 3 memory accesses to DRAM and NVRAM in total per demand request. But this is highly dependent on the implementation of the DRAM cache. And so, therefore, in order to understand how access amplification manifested itself for this specific DRAM cache implementation, as well as the bandwidth performance of this device, we were then motivated to develop a custom suite of micro benchmarks that tested or targeted a variety of different operating modes, dirty misses, clean misses, so on and so forth. And then we utilize performance counters of the hardware in order to capture the traffic generated by these micro benchmarks. And from these micro benchmarks, we had found that this DRAM cache implementation in the Intel server experienced much higher access amplification than that simple example or simple implementation I went over just before. If you focus your attention on the LLC write miss dirty, you'll see instead of 3 times like we saw with the simple implementation, we observe 5 times the access amplification. And I'll be using this as an example of how we actually derive these results. Looking at the data from this specific micro benchmark where we had 100% write dirty misses to DRAM, I want you to focus your attention on just the right portion of the graph for now, because what we derive from this will be applicable to all the other random axes you see over there. But the idea here is if you focus on the purple bar, this represents the effective bandwidth from the programs. This is the effective bandwidth of the program. So ideally, this is how much data the program thinks should have been moved, which we calculated by logging the amount of data the microbenchmark itself accessed and divided that by the wall clock time of the program. So you can think of this as the demand requests made by the program. And what you'll notice is that the DRAM read, NVRAM read, NVRAM write, they have equal amount of bandwidth as the effective bandwidth, suggesting that for every demand request made from the program, or every time the program tried to access some piece of data, there was one DRAM read, one DRAM write access, and one NVRAM read access. But you'll also notice that the DRAM write bar itself is twice the length of the effective bandwidth, here suggesting that we had twice the number of DRAM writes for every demand request. Therefore, in total, showing for this dirty miss writes 5 access amplification. Surprisingly, though, we found that the access amplification exhibited by the DRAM cache also had a negative effect on the NVRAM bandwidth itself. From our benchmarks, or microbenchmarks, we had identified that the achievable read bandwidth of the NVRAM could be 30 gigabytes per second, and the achievable write bandwidth, 11 gigabytes per second. But when we ran our microbenchmarks with 100% clean misses, for example, for the read bandwidth, we observed a drop to 23 gigabytes per second, and for the write bandwidth with 100% dirty misses, 8 gigabytes per second, showing a significant drop in the bandwidth utilization here, and suggesting that an application here would be limited from or be prevented from fully utilizing the NVRAM read, NVRAM write bandwidth if it exhibited a high miss rate to the DRAM cache. And so from these micro benchmarks, the insights we gathered are that, well, this DRAM cache can exhibit up to 5 times the access amplification per demand miss, as well as the fact that this access amplification has a negative effect on the NVRAM bandwidth, and showing that with a high miss rate, we get poor bandwidth utilization. But it's also important to note that for these micro benchmarks themselves, these are examples of the ideal workload characteristics and do not account for things like latency, thus suggesting that in a real workload, these bandwidth numbers would be much worse. And thus, we conclude based off these insights that for workloads greater than or in capacity greater than the size of the DRAM cache, the DRAM cache performs fairly poorly. We then wanted to take these insights, see if they occur in a real workload, and show the implications of these insights on their performance. And so for our real world workload, we decided to use graphs because one, they're a great example of a workload that is growing in size, but two, they, because of the fact that they are infamous for having this irregular access pattern, and so it makes it hard for software to optimize the performance for these sorts of workloads. For the specific engine itself, we decided to use Galois because Gill and Co. had shown that Galois was the state of the art in comparison to all other graph frameworks when run with the hardware managed DRAM caches. We also wanted to have an example of a working set that fit in the DRAM cache and didn't fit in the DRAM cache. So we chose WDC12, a realistic graph that is the largest publicly available graph out there and that greatly exceeds the capacity of our DRAM cache. as well as we generated a Kronecker graph to ensure that we had an example that fit within the DRAM cache. And all results from the evaluations were collected by using a hardware performance counters again. And from our experiments, we calculated or we measured the bandwidth performance of when our graph or when our working set fit within the DRAM cache, as well as the bandwidth performance when it didn't fit in the DRAM cache. And you can observe here a significant drop when the data or the working set exceeds the size of the DRAM cache capacity. Specifically looking at just BFS alone, we observe more than a 50% reduction in bandwidth utilization. And to understand why this bandwidth utilization occurred, we then also captured a trace of the tag statistics for the graph WDC12, a graph that doesn't fit within the DRAM cache. And we also captured the bandwidth trace of the same graph. And we find a strong correlation with the tag hits and misses to the bandwidth performance. And you'll also notice that with the tag statistics, there are a low amount, a modest amount of tag miss clean and tag miss dirty in our workload. Yet we suffered a severe drop in bandwidth performance, showing that, well, even with just a modest miss rate, these graphs experience poor bandwidth utilization. We then wanted to ask the question, okay, how much data is actually being moved when using the DRAM cache? And so in order to answer that, we wanted to capture the baseline data being moved, or the amount of data that was from the program, how much data should be moved, by running the same experiments or evaluations for the graph that didn't fit within the DRAM cache in 1LM mode, where the DRAM was then configured as our main memory, and we configured the NVRAM devices as extra Newman nodes, so that when the DRAM overflowed, the NVRAM would be populated with that data. And ultimately, what we found, here you'll see the top is the data moved when our NVRAM devices are extra NUMA nodes versus when we're using the DRAM as a cache, and we see a significant amount of unnecessary data being moved when the DRAM cache is being utilized, which we attribute to access amplification as we described above or beforehand. So hopefully what you take away from this is that in these real world workloads too, just a modest amount of dirty misses and the bandwidth utilization tanks, as well as the current implementation of the DRAM cache seems to exhibit high access amplification, and ultimately showing that the DRAM cache does not work with these working sets larger than the DRAM cache capacity. And now that you know that the DRAM cache doesn't work so well in these terabyte scale systems, we'll now go over sort of what others have done to circumvent this problem, as well as what future direction we could take. And so one technique has been to take advantage of software to manage the movement of data. Specifically, with AutoTM, our group showed a way to accomplish this with training of CNN models by taking advantage of static information about the neural networks in order to optimize the movement of live tensors. And we showed from this technique that you can achieve a performance improvement of 3 times over hardware managed DRAM caches. With Dulapala and Co., they showed with Sage a way to perform the similar optimization for graph analytics by partitioning the data such that all mutations to the graph only ever occur within the DRAM cache, and the NVRAM devices were only allocated towards read-only data, where they had found with this technique a 1.94 times speed up over the state-of-the-art Galois. But these approaches are limited by the fact that they rely on the CPU cores in order to move the data, as well as the fact that this also makes it difficult for them to transfer data asynchronously. They're also limited by the fact that these are highly specialized. They require specialized knowledge in order to make these sorts of modifications, and therefore is not generally applicable to other problem domains. And so ideally, we would like is to take advantage of that high level knowledge that the software has over the program of the access patterns, as well as the hardware acceleration benefits of the system itself. So then we ask the question, can we have both? Can we come up with a solution then such that a programmer requires very little modification, or we have a solution that is applicable generally, yet at the same time is high performance at the same time? And with that question in mind, I want to also acknowledge Intel and thank them for providing the system we had for this work.